Hi all, today we are going to cover chapters 7 and 8. Chapter 7 is over the central limit theorem, which is a really important theorem that helps us be able to do what we're going to do in chapter 8, which is confidence intervals. So let's go ahead and get started. So this is an introductory slide you can read on your own. Now, this is the formal definition that our book gives for central limit theorem. Again, you're very capable of reading it on your own, so I'm going to give you a few minutes to do so. Now, the big idea here that I want to make sure that y'all understand is that we have to have sufficiently large to be able to make these Lord Jesus, assumptions. And so we will talk about what sufficiently large means, but usually, in most cases, it's greater than 30. So this gives a kind of comparison of what that central limit does for us. It takes the population distribution, and as the population gets larger, as the sample gets larger and larger, it makes the sample look more normal. So here are just some parameters. So we have our mean, which is mu if you're talking about the population, or x bar if you're talking about the sample, and then the standard deviation, which is sigma if you're talking about population, and s if you're talking about sample. These are all symbols we've used in the past. And you'll see this formula is very close to what it looks like for a z-score. The only real difference is we are now taking the square root of the sample under the standard deviation when we are working these types of problems that fall into this particular set. So the central limit theorem comes from the law of large numbers, which essentially tells us that the larger our numbers get, the more likely they are to converge to a particular distribution. And so that is exactly what is happening here. So please pause the video and read the law of large numbers. All right, so this is some pictorial representation showing you how that central limit theorem kind of works in our favor when we're talking about these distributions, and how increasing the sample size makes our distributions look more normal. So you see, we started with a normal distribution here, and as our samples got larger and larger, our graph changed but looked normal. In this case, we started with a uniform distribution, but again, as long as we took our samples and our samples got larger and larger, we became more normal. You can see the same thing happens when you're talking about a right skewed graph, and it would work the same with a left skewed graph. So this shows you that we are basically still using the normal distribution in these calculations. It's just now it's our sample of samples that we are talking about that is normally distributed. So this shows again how as the sample size increases, the more normal our graphs take a shape of. And so the rest of the slides are pictorial representations that kind of just continue to outline that same idea of as sample size increases, our distribution becomes more normal. So you can pause each slide and read it for yourself. And then here we can see that we are told how to find our population distributions for our sample and sampling distributions based off of different parameters. So let's jump into chapter 8 because that is where the actual problems that you'll be doing on homework and in your midterm are going to be located. All right, so a confidence interval is basically an interval that we can use as an estimation. So we know that we can use the mean as a point estimate, but that estimate can only be correct or incorrect. If we use an interval, that increases how much our estimate is, how many values there are to choose from for the estimate, and so it makes it more likely that we will be correct in our estimations. And you can see that confidence intervals are based off of the normal distribution, and that's why the sample size is so important, because we need the normal distribution to be able to do these confidence intervals. And so making sure you have a large enough sample size is what we need to do to make sure that we can do these confidence interval problems. So this is the critical values of Z. This is a helpful table for you. A lot of times, if you don't have this table, you need to calculate that critical value by hand. We're not doing anything by hand. We're going to be using Excel. So you should be able to work from there using Excel. So let's take a look at this first example. Suppose we're interested in a mean score of an exam. A random sample of 36 scores is taken and gives a sample mean of 68. In this example, we have the unusual knowledge that the population standard deviation is 3 points. Do not count on knowing the population parameter outside of textbook examples. Find a 90% confidence interval for the true population mean of the statistics exam score. So we know that we can do this because we have a sample greater than 30. We're given the sample mean, and then we're given the population standard deviation. We're going to do 3 different types of confidence intervals today. One's going to be a mean when we know the population standard deviation, which is not usually the case in real world examples. The second is going to be confidence intervals when we do not know the population standard deviation and instead use the sample standard deviation divided by the square root of the sample size as our estimate. And then we'll be using it when we're looking at problems that contain percentages. So let's look at how to use the Excel program that I provided to you to be able to do this problem. So give me just 1 second to share my screen. Okay, so I'm going to open up the Excel. This is the same document I provided to you in Blackboard, the Midterm 2 Excel program. And you see there's several tabs here. We have confidence intervals, Z-test, T-test, one-prob Z-test, and linear regression. Now, what I want you to be aware of is that we are going to be doing confidence intervals in today's lecture. So we're going to do everything in this worksheet here. How this worksheet works is what happens is we put in into the green values. So we're only entering things into these green cells. Everything else is either being calculated or it's an output. So you see there's 3 different ones here to start with. There's PROP, which stands for proportion. There's mean pop unknown standard deviation, and there's mean pop standard deviation known. So that POP stands for population. So this first type we're doing for the mean pop standard deviation known. So we're going to enter our information into this box of green here. So the first thing we're being asked is the confidence. So we're told that the confidence is 90%. So the confidence level is 0.90, the decimal form of 90%. We're going to fill in the population standard deviation. So the population standard deviation that was given to us in this example was 3 percentage points. Our sample size was 36. And the sample mean that was given was 68. And now you see that right here in blue, we have been given an interval, the interval that goes between 67.18 to 68.82. So that is the solution to the problem. Now we can write that solution a couple of different ways, and you'll enter it into your homework a couple of different ways. The first way is just as an interval. So if we enter it as an interval, it would be 67.18 to 68.12. Oh, what did I say? 68.82. So that's one way to write the interval. Another way to write the interval is in a different form. And this form is helpful because it reminds us of what we're estimating here. So we're going to have 67.18, which is less than or equal to the population mean, which is less than or equal to 68.82. So this way shows us what we're estimating, and we again are estimating the population mean here. This way, we aren't clearly stating what we're estimating, so it's not always the best way to do it. So just keep that in mind when you're working on your homework. There are 2 ways to input correct solutions, but your homework may ask for a particular way, so be aware of that. So for this next one, it says, suppose we had changed the original problem in example 8.1 by using a 95% confidence level. Find a 95% confidence interval of the true population mean statistics exam score. So this one, we could be asked to adjust for a different confidence interval. And in that case, all you would do is go in and change the confidence level because we didn't change anything else in the problem. So the new confidence level would be 0.95. When you do that, you see your values over here change. So 67.02 to 68.98. So here we would say 67.02 is less than or equal to the true mean, which is less than or equal to 68.98. So here, what's happening on these confidence levels is this change in the confidence interval, is that the area is getting bigger or smaller based off of what your confidence level is. So you are making your interval either wider or narrower. So let's take a look at 8.3. Suppose we change the original problem in example 8.1 to see what happens to the confidence interval if the sample size has changed. Leave everything the same except for the sample size. Using the original 90% confidence level, what happens to the confidence interval as we increase the sample size and use n equals 100 instead of n equals 36? What happens if we decrease the sample size to n equals 25 instead of n equals 36? So let's take a look here. So this time I'm going to go back and I'm going to change this back to 0.9 because that's the original confidence level. We saw when our sample was 36 what the answer was. If we increase our sample size, we see that it changed a little bit. It's now 67.51 to 68.49. So let's record these so we can look at them at the end. So when n equals 100, my confidence interval is from 67.51 to 68.49. And then if we decrease it down to 25, we get 67.01 to 68.99. So when n is equal to 25, our confidence interval becomes 67.01 to 68.98. So you can see here that when you have a smaller one, it's wider, and when you have a larger, it's narrower. And that's because the larger it is, the more chances you have of being exact. Okay, so this talks about a new distribution which we haven't discussed before. This is called the student t-distribution. It is a lot like the normal distribution. The only real difference is instead of being measured by its mean and standard deviation, it is measured by its sample size, which then is changed to find a degree of freedom, and we use it that way. Now, the only real difference in the pictorial representation between a student distribution and a normal distribution is the amount of area that's in the tails. So it's still a bell shape, it's still symmetric, it's just the tails are larger on a student t-distribution. So it's important to realize because of the central limit theorem, as the sample size gets larger, then the normal distribution becomes more. Well, sometimes we can't get a large sample size for whatever reason. It could be funding, it could be it's too specialized. There's lots of reasons why you might not be able to get a sample size that's greater than 30. And in that case, you would want to use the student t-distribution because it gives you more area in the tails to work with. So let's take a look at this. The average earning per share for 10 industrial stocks randomly selected from those listed on the Dow Jones Industrial Average was found to be X equals 1.85 with a standard deviation of S equals 0.395. So it's important to realize here that this is in the case where you do not know your population standard deviation. You are using your sample standard deviation here because you have S equals. And we want to calculate a 99% confidence interval for the average EPS of all industrials listed on the DJIA. So we can do this problem. The only difference is now we are using a different block on here. We are now doing the mean population unknown standard deviation. So it is based off of using the t-distribution. So we can put in our given information. So we were told that the confidence interval was 0.99. The sample mean that we are using is 1.85. The sample standard deviation is 0.395. And the sample size is 10. And you can see once I enter that, I get a final solution here. So we have 1.444 to 2.256. So our confidence interval here is that our true population mean will fall between 1.444 and 2.256. Now, your homework may ask for a particular rounding, right? So if you go in here and your homework says, okay, instead of rounding to 3 decimal places, I want you to round to 4 decimal places. All you have to do to this program is highlight your answer here, and you can increase the number of decimal places by clicking this button here, or you can decrease decimal places by clicking this button here. So that will help you not have rounding errors when you're working on your homework, if the rounding is specified. All right, so this is one that you can try on your own. It says you do a study of hypnotherapy to determine how effective it is to increase the number of hours of sleep subjects get each night. You measure hours of sleep for 12 subjects with the following results. Construct a 95% confidence interval for the mean number of hours slept for the population, assumed normal, from which you take the data. So in this case, what I'm going to do is I'm going to first start by inputting into my Excel document, but I'm going to input all of these values. So let me show you how this is going to work. I'm going to put in the data that's listed into this raw data right here. So if I put in the raw data that's given, I was told it was 8.2, 9.1, 7.7, 8.6, 6.9, 11.2, 10.1, 9.9, 8.9, 9.2, 7.5, and 10.5. So now you will see over here, it gives us from the raw data our sample standard deviation and our sample mean. So when we're given raw data, we should know that we need to go in here and we're going to be using this mean population unknown standard deviation because we're going to use the sample standard deviation that comes from our raw data here. So the confidence interval we were asked for was 95%, so we're going to put in 0.95. We're going to put in the sample mean. I'm going to round to 2 decimal places, so 8.98 is the sample mean that came from our raw data. I got that right here. And the sample standard deviation is 1.29. And then we had 12 value points for raw data. If you're not sure, just look over here. It's one less because we have raw data titled than here. So then when I click enter here, I get my confidence interval. So 8.16 to 9.80. So here, the solution is 8.16 is less than or equal to the population mean, which is less than or equal to 9.80. Now, the last type of confidence interval we're going to work with is the population proportion. So this goes over population proportion and how to computate that confidence interval, how to compute that confidence interval by hand. But again, we're going to be using the Excel program that I provided to you. So let's just jump straight in to how to identify our variables and how to put it into the Excel document. So suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. 500 randomly selected adult residents in the city are surveyed to determine whether they have a cell phone. So in here is 500 because that's how many are surveyed. Of the 500 people sampled, 421 responded yes, they own cell phones. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of adult residents of this city who have cell phones. So in this case, having a cell phone is our success. So we have 421. Now, that means that we could find our p-hat. Our p-hat, which is the point estimate we're using, is 421 over 500 in case we need that information. Now, when we are asked for the confidence interval here in the program, we don't have to have p-hat. I'm actually going to calculate p-hat for you right here. So the confidence level that we were asked about was 0.95. The amount of people who had cell phones was 421, and the amount of people we sampled was 500. You can see you get a p-hat here in decimal form, and you get your confidence interval right here if you needed either one of those. So in this case, we have 0.810 to 0.874. So when we write our answer, again, we can write it two ways. We can write it in that parentheses where we have 0.810 to 0.874, or we can write it using identifying what we're estimating, right? Which is a lot of times pretty important. So here we have from 0.810 is less than or equal to our population proportion, which is just P, which is less than or equal to 0.874. So this is another way we can write that. So let's try another one. A financial officer for a company wants to estimate the percent of accounts received that are more than 30 days overdue. He surveys 500 accounts and finds that 300 are more than 30 days overdue. Compute a 90% confidence interval for the true percent of accounts receivable that are more than 30 days overdue and interpret the confidence interval. So what this is saying is our N is 500, our X is 300 because that's how many are overdue, and our confidence level is 0.9 because we're using 90% confidence interval is what we're being asked for. So we jump over to our Excel document and we can input 0.9. Our X was 300. Our N was 500. And so our confidence interval is 0.56 or 0.564 to 0.636. So we're looking at it being 0.564 is less than or equal to our population proportion, which is less than or equal to 0.636. So when it says interpret the confidence interval, what that means is, what is this saying? This is saying that approximately 56.4% to 63.6% of all accounts receivables are overdue. So that's what it means. So sometimes we want to estimate the sample size we're going to need. So we can manipulate our confidence interval information to find out some sample size. So you can pause this to read the idea behind it. And this shows you how we calculate sample size if we have some information about what we want. So this is really helpful. Let's say that you are at work and your boss wants you to do a study over how many people are reacting poorly to their insulin shots. Let's assume you're a doctor and you're doing this study, and you're using a sample of your patients. Well, you want to know how many patients you need to sample because your boss tells you that he wants a 95% confidence interval. And you have to know how big of a sample you need to guarantee or to get you pretty confident on what's going on here. So let's take a look at an example. Suppose a mobile phone company wants to determine the current percentage of customers age 50 plus who use text messaging on their cell phones. How many customers aged 50 plus should the company survey in order to be 90% confident that the estimated sample proportion is within 3 percentage points of the true population proportion of customers age 50 plus who use text messaging on their cell phone? So I also built this into your Excel document. You just scroll down and it is here. And so you're always going to round up for these. So that's why this little note is right here for you. And we're going to take the information we're given, put it here. So it doesn't tell us what the current proportion is. Or a current standard proportion. It doesn't give us a proportion we're using. So anytime it doesn't give you a proportion that you're using, you're going to use 0.5 in these type of problems. Your standard error here, or sample error here, which is what SE stands for, is how many percentage points you want to be within. We want to be within 3 percentage points. And the confidence level we were asked for was 0.9. And so, let's see. Oh, I didn't put, that should be 0.03 because we want percentage points. Okay, there we go. And so we would need to sample 752 people to guarantee that we have a confidence interval that is within 3 percentage points. Okay, so I realized that there was some kind of issue with recording. I'm going to go over that one more time as far as how to use the Excel. So you're using this sample size predictor here. If you don't have a proportion given to you to start with, you're going to use 0.5. We want 3 percentage points. We want to be within 3 percentage points in our confidence interval. So we're going to use 0.03 because it is percentage points. And then our confidence level is 0.9. When we enter all that, we get 751.5. Well, we can't sample a portion of a person, so we're always going to round that up. So it's 752. So in this case, we need our sample size to be equal to 752. All right, that is the conclusion of chapters 7 and 8. I will see you next time for chapters 9 and 13.